All right, so today we're going to talk about rotational spectroscopy. Yay, we're going to switch gears. So we're going away from the sort of the theoretical side of things where we're just talking about wave functions and the transition dipole moment integrals and so on. And we're going to start talking about specific spectroscopic techniques. Like the last lecture we did vibrational spectroscopy. So today we're doing rotational spectroscopy. So really for our course and in your experience, there's going to be three major areas of spectroscopy. There's UV vis, there's IR, and then this is microwave. You probably won't get into microwave, but in the infrared, sometimes for gas phase molecules, we see rotation and vibration coupled together. So you can't understand ro-vibration, where rotation and vibration are combined, without understanding just rotation by itself. So even though we're not going to see rotational spectra by themselves, this will help us prepare for the carbon monoxide lab, where we're actually getting rotational spectra in the infrared region. So let's look at that rotational spectroscopy. So these are the rotational energy levels. So the quantum number is J for rotational motion. And so this is the energy level equation, B times J plus 1. And that's just the way they write it. They could write B times J squared plus B times J, but this is the traditional way to write it. So you have some rotational constant out front, B, and then you have the quantum number J times J plus 1. So those are the energy values that come out of the Schrodinger equation when you solve for that for rotational motion. And what is B? Well, it's this rotational constant up here. And you see it looks very familiar. It looks very similar to the particle in a box piece that comes out of our energy equation. You have Planck's constant in the numerator. For a particle in a box, it was h squared. Here it's h. You have an 8 in the denominator, and you have in the particle in a box a mass in the denominator. Here you have I, and I is the moment of inertia for rotation. Okay, so this moment of inertia has mass in it. It's the sum of all of the masses of the particles that are rotating times their distance from the rotating axis. So it's not necessarily bond length, it's the distance from the rotating axis. So in this case, if you have a diatomic, you have two masses, and you have their distances from the center of mass. If you have a molecule like water, and it's spinning around the C2 axis, it's not the OH bond length, it's the perpendicular length to the rotation axis here. Okay. And so that would be what you would calculate the moment of inertia for this motion as this proton mass times this distance here squared, and then this proton mass times its distance squared. And so that's the moment of inertia. The oxygen wouldn't have a contribution to the moment of inertia for this rotation because it's right on the axis. So its distance from the axis would be 0. And it gets more complicated from there. So in a larger molecule like ethane, you've got all kinds of things. So you can add up all of these distances from the rotating axis and come up with the moment of inertia for this particular molecule here. Notice I've drawn dipole moments on water and on this, I would say, carbon monoxide molecule. Okay, and so this is important for you to understand for rotational spectroscopy what a dipole moment is. And so we draw the arrow like this with a little plus on the positive side. Okay. And so if you've got, let's say you have a carbon over here and an oxygen over here, and the oxygen pulls electron density towards it, then you've got a positive side of the molecule and a negative side of the molecule. So like in organic, they put the partial charges on there. And so we draw the dipole moment indicating this dipole. There's a positive end of the molecule and a negative end of the molecule, and this is a polar bond. Okay. Same with water. This dipole moment goes up and down. So here's the oxygens pulling electron density towards the oxygen, leaving those hydrogens exposed, and that's what makes water acidic. Okay. Also makes water basic because you have electrons on the oxygen, so it can accept a proton on the oxygen. It can donate a proton over here from the protons, but it has this vertical dipole moment. A molecule like ethane, even though it has polar bonds like this, each one of these bonds is a small dipole. But because of the geometry, they all cancel out. And so this molecule does not have a net dipole. And so this is one of those situations where you can have polar bonds, but the molecule as a whole is nonpolar. That's important for rotational spectroscopy, and we'll talk about that in a minute. So let's look at the energy landscape. So the electronic energy levels, what do we have with an electron? We have a tiny little mass, and mass is in the denominator. So the energy levels are really far apart. So for electronic spectroscopy, you have high energy transitions, really large arrows, which gives us really short wavelengths. So the wavelengths here are in nanometers. Okay. Then if you were to zoom in, like if it was Google Maps and you start scrolling the wheel and you get closer and closer to this ground state, you would start to see vibrational levels. So way down here, you would see the vibrational levels for that electronic state. And then you have all of these, and this is in the infrared. So this is wavelengths in the micron range. Okay. And that's the vibrational energy levels. Here we've got a couple of vibrational modes. You can have different excitations, you can have overtones, and so on. What if we scrolled in the wheel a little further, like if it was Google Maps, and zoomed in on this ground state, what would we see? Then we would see the rotational levels. So I just want you to get an idea. You got a huge difference in the electronic energy levels, then vibration is really small, close together, and rotation is even smaller and even more close together. And that's in the microwave region, which has wavelengths in the millimeter range. So you go from nanometer wavelengths to micron-sized wavelengths to the -6, and then 10 to the -3 millimeter wavelengths in microwave. And that's where we do pure rotational spectroscopy. You see the quantum numbers with J's. Okay. The thing that we have in rotational spectroscopy that we really don't have in vibration or visible is we have a lot of thermal excitation in those rotational levels. So just at room temperature, if these energy levels are, 5 or 10 wave numbers apart, and we have 200 wave numbers at room temperature, we have a lot of thermal excitation in the rotational energy levels. So that's one thing that's unique about rotational spectroscopy is there's a lot of hot bands because we have a lot of molecules that are thermally excited. So light must be able to interact with this rotating molecule for absorption to occur. Okay. And what is the handle of light? Light is an oscillating dipole. So the molecule has to have a permanent dipole because all we're doing in rotational spectroscopy is we're rotating the molecule. So it's spinning around in space. If there's no dipole on the molecule, light has nothing to grab hold of. So if there's a positive and negative in and it's rotating, now the positive is pointing down. It rotates again, now the positive is pointing up. So that rotating dipole is what gives it an interaction with an oscillating dipole, that is light. If there's no dipole in the molecule, then light won't even see it. It'll just pass right through. So O2 and N2 are transparent to microwave radiation. And that's what helps us get rid of the heat. You've heard of the greenhouse effect? Okay. What causes the atmosphere to absorb the light? That the sun, visible light, and all kinds of wavelengths hit our Earth. The visible and UV get converted into molecular vibrations and so on. And then the molecules, as they relax, the ground cools, it's emitting infrared radiation. That infrared light goes right through nitrogen and right through oxygen because nitrogen and oxygen don't have a permanent dipole. So this is how we get rid of the heat from the sun. But if we have water in our atmosphere, then that water can absorb some of that microwave radiation. And that keeps us from freezing at night. So the greenhouse effect is great. What's bad is a runaway greenhouse effect. Okay. A runaway greenhouse effect keeps that heat in, and then the next time the sun comes along, we just stack up heat upon heat. Okay. So this greenhouse effect is based upon the transparency of nitrogen and oxygen and the non-transparency of water. CO2 has some effect too. Okay, but water is the most important greenhouse gas that keeps us from freezing at night. And so that's what's going on. So water has that dipole moment. So therefore, this molecule must possess a permanent dipole moment. So all polar molecules possess a dipole moment. And so they will have a pure rotational spectrum. But N2, O2, no dipole moment. So they do not possess a pure rotational absorption spectrum. Now the selection rules are plus or minus 1. So the change in rotational quantum number is plus or minus 1. Now we might ask the question why, and how did we come to that conclusion? Well, we could go through the math. We could do the transition dipole moment integral for rotational motion. It would be kind of messy, especially if it's in 3 dimensions. Okay, but we could do it in 1 dimension, and we could come up with that value. But we could also just think about it. So rotational motion has angular momentum, and light has 1 unit of angular momentum. So when light comes in, it can impart one unit of angular momentum to the molecule. It could also cancel 1 out, so that would be a delta J minus 1. And then here's the transition energy equation. So E to the J plus 1 minus E of J gives us this transition equation. So this is the equation for where the peaks show up in the spectrum. So this is the spectral line equation, the horizontal axis of the spectrum. So why plus or minus 1 on J? We have the molecule here, and we have light. And you could also think of light as having circular polarization. A lot of times we talk about plane polarization light, so light polarized along the x-axis or along the y-axis, and it's traveling in a certain direction. So that gives us a plane. So we call it plane polarized light. But you could also have light that is circularly polarized. And that's one way of thinking about this unit of angular momentum. So it's oscillating field, say it's positive up here, and that positive charge is rotating for light. And so it has 1 unit of angular momentum, and that could rotate at the same speed as a rotating molecule. And so it could give it a kick. And so you see here light with rotating polarization interacts with a molecule that's spinning, has a dipole moment. And now up there you see 2 little arrows. So it's giving, 2 units of angular momentum to the molecule. And so since light has 1 unit of angular momentum, it can be added to the molecule. It could also be subtracted. And so if light's going in the opposite direction of the molecule, it could slow it down from spinning by 1 unit. And since Raman transitions involve 2 photons, what do you think the delta J selection rules are for Raman spectroscopy? Yeah, plus or minus 2 and 0. So they can be in the same direction. They can be in opposite directions, or they can be in the reverse direction. And so this would be plus or minus, or plus 2, 0, and minus 2. So it's not just plus or minus 2. Scattering is also possible with Rayleigh scattering. So Raman is the plus or minus 2, and Rayleigh scattering is the 0. Now, I didn't really like this. And as I was teaching physical chemistry, I thought, we've been using symmetry this whole time to come up with our selection rules, right? It reduced 4 pages of calculus down to a Post-it note by using symmetry, if we understand the wave functions. So I thought, what if we could use the rotational wave functions and just look at the symmetry of those and come up with this plus or minus 1 and a plus or minus 2 and 0 for scattering. And so I had a student look into that. That was her undergraduate work for her research. And then she stayed and got her master's. And so this was Victoria's pen. And so we wrote this paper for chemical education where we used the symmetry of rotation to come up with the selection rules instead of this taking, in PChem we were doing symmetry, and we get to rotation, we start talking about angular momentum. And I know most students are not analytical enough to sit here and go, no, wait a minute, you were using symmetry arguments this whole time, and now you're talking about angular momentum. But as a professor, it bothered me. It's like, that's inconsistent. Symmetry is everything until we get to rotation. Now all of a sudden we're talking about angular momentum. Okay. And so we wanted to see if symmetry arguments would work as well, and they do. So that's great. So we wrote this paper. She published her thesis. She graduated with her master's, yay, and we put that in the book. So she's my co-author for the book, and we took the particle in a box, and we also did particle on a ring. So those chapters that are in that book dealing with rotational motion have this in chapter 9, where we use symmetry to argue for the rotational selection rules. And I think that's a good contribution to science because we couldn't find anybody that had done that before. So that was pretty exciting. As you can see, he's jumping. Okay. So this pure rotational absorption spectrum, again, whenever we're dealing with a spectrum, the spectral lines are differences in energy levels. And so look how close the energy levels are for rotational motion, lots of thermal excitation in those levels. And so this is why we see lots of hot bands. One of these is the fundamental, the rest are hot bands. And so these transition frequencies are separated by 2 times the rotational constant. And so the spectrum gives a lot of measurements of B, right? So in your lab, even though you're not going to be dealing with pure rotational spectra, your ro-vibrational spectrum will look very similar to this. And you will assign quantum numbers to all of those. And then you'll put those in a spreadsheet, and you'll have the spreadsheet calculate the trend line, right? So there'd be a slope with respect to quantum numbers. So you have quantum number as your X values, and your Y values are the frequencies, and you see what's the slope, and the slope is 2B, okay? So subtract the 2, and you get B. So you have lots of measurements of the rotational constant in your spectrum. So this gives you a really good average and a really good standard deviation. So that means you're going to have lots of significant figures, right? If you've got a crummy average, you might have 2 significant figures. If you have a really good standard deviation, it's out in the 4th or 5th decimal place. Now you've got 6 or 7 significant figures. And then when you calculate the bond length, then you'll have also 6 or 7 significant figures. So this is really good for bond lengths and angles. But the problem is for larger molecules, there's only 3 rotational constants. Okay, why is that? Why in any molecule, no matter how big, are there only 3 rotational constants? Rx, Ry, and Rz. Yeah, so rotating around X, rotating around Y, and rotating around Z. So a nonlinear molecule has 3 rotations, no matter how big it is. Okay, so we could do rotational spectroscopy on a molecule, but we would only be able to solve for 3 rotational constants. And it would be some combination of all of those distances from the rotating axis. So it gets really complicated for a bigger molecule. Okay. So there's no maximum number of bonds, angles, and bond lengths. Okay, but symmetry does help because you could say that all 3 of these distances are the same if the molecule is symmetric and so on. So you might be able to come up with only 3 unique variables in a larger molecule if it's very symmetric. Like you could say if benzene, all those carbon bonds have the same bond length, then all you need to do is solve for the carbon-carbon bond length, and it's the same for all 6 of them, and the same for the carbon-hydrogen bond length. So you have 1 bond length for all 6 carbon-carbon distances and 1 bond length for all the CH distances. So in benzene, you could define the whole molecule with just 2 bond lengths, even though it's got 12 atoms. Okay, so symmetry really helps. So if we could get the rotational constants for benzene, we could totally solve for the structure for benzene because it really only has 2 bond lengths. Now for Raman spectroscopy, I should say scattering is a 2-photon process. So there's Rayleigh scattering and Raman scattering. The Raman scattering is the inelastic scattering. The incoming photon and the outgoing photon are different energies. Okay. For Rayleigh scattering, the incoming and outgoing are the same wavelength, same energy. So this would be the delta J equals 0, and this would be the delta J plus or minus 2. And so we would have a red shifted or a blue shifted photon. And so this is what the pure rotational scattering spectrum looks like. Now for Raman, you don't need a permanent dipole moment. So you could get a Raman spectrum of nitrogen, N2 or O2 or H2 or any of those. Okay. So light interacts with the polarizability of the molecule. So it's shaking the electron cloud. The electron cloud is oscillating with the visible light. It's in that range. It's in the range of nanometers of wavelength. And so then this oscillating electron cloud would oscillate differently if the molecule were rotating. And so with the rotating molecule, you get a different kind of oscillation of the electron cloud, and that interacts with the visible light and can scatter that visible light. Okay, so no dipole is needed, and the scattering selection rules are 0 plus or minus 2. So the Raman transition equations for linear molecules are the laser line, the whatever the incident laser is, it comes in, and that's the Rayleigh line. So if you're standing off axis and you're looking, so the laser's coming through here, you're looking at sideways, you're going to see a lot of green light that scatters into your detector because that's the laser, and it's just bouncing off the molecule, no change. in the wavelength of light. But for the Stokes, the red-shifted laser line, you have the laser line minus this piece, and this piece is related to the rotational energy level changes. And so it's 4 times B times the quantum number plus 3/2. So this is our differences in the energy levels. I mean, differences in the spectral lines in a Stokes rotational Raman spectrum. And then for the anti-Stokes, where the molecule is relaxing and giving some of its energy to the laser line, so you get blue shifted light coming out. It's shifted by this 4B times J minus 1/2. But you notice the slope. If we were to assign all of these lines a particular J quantum number, and then we were to, in Excel, take that column of J quantum numbers and add in 3/2 to the Stokes lines, or subtract 1/2 from the anti-Stokes lines, and then look at the frequency at what's the slope of that frequency with respect to this J minus 1/2. This is the slope. This is the factor in front of it. And so we will be able to solve for that rotational constant B. So once we have B, then we can solve for bond lengths and angles. Now this is really close to the laser line. This is, again, the energy level differences are really small, and so the spectra show up really close to the laser line. And so that's what makes rotational Raman really hard, because you need a very high resolution, narrow laser. So most of our lasers that we have, our little diode lasers, the width of the laser line and the Rayleigh scattering line is wider than this whole range. So we would not be able to resolve the rotational spectrum with our cheap lasers. For pure rotational Raman, you need a pretty high dollar laser, $100,000 laser. Our lasers are $14,000. So it's not something that we can afford. And plus, we wouldn't use it very much. But still, to do pure rotational Raman, you need a pretty expensive laser that has a very narrow line width. The way you get a narrow line width laser is you move the resonant cavity mirrors further and further apart. Okay, so you're selecting a particular angle for the lasing effect to happen. And we'll talk about lasers when we get to electronic spectroscopy, so another couple of weeks at least. But what you have is you have a resonant cavity for the lasing effect, and the further apart those mirrors are, the more selective you are in terms of the angle at which that lasing effect happens. And you're selecting a certain number of wavelengths between those mirrors. So we just don't have that kind of laser setup. We did in my graduate school days. It was really nice. We had some high resolution lasers. So let's do those transition equations. We've talked about the transition equation. Let's just do the algebra for a couple of them. So let's look at just the absorption transition. So delta J plus 1. So here's how we do that transition equation. So we set it up this way with E of J plus 1 and subtract E of J. So wherever here's the energy equation. So wherever there's a J, we put a J plus 1. And so that's what we have here. We have a J plus 1 times J plus 2. You see how that's J times J plus 1. So wherever there was a J, we put a plus 1. And then we subtract the energy equation without changing it. So this is the delta J plus 1. So just multiplying through, we have J squared plus 3J plus 2. We could multiply B through all of those. And so the B squared terms cancel. So we got a minus B squared and a B squared here. We have a B times J here. We have 3 of those here. So I'm going to make this a 2. And I'm going to cancel that one. All right. And then I can pull the 2B out of this. I have 2B times J plus 2B. So I'm going to pull that 2B out front. And I have 2B times J plus 1. So that's my transition equation. And what I'm trying to show you is that B value has the mass of the particle in it and the bond length information. So if we're dealing with a diatomic molecule, it's super easy to solve for the bond length. And that's what you guys are going to do. All it requires is to come through here and assign the quantum numbers. So like 0, 1, 2, 3, 4. Okay, so what I mean by making this 4, that's like the 4 to 5 transition. That's what I mean by labeling that one 4, right? And labeling this one 5 would be the 5 to 6 and the 6 to 7 and so on. So what we're doing with labeling those peaks, that's called peak picking. So you will go in and you will pick the maximum peak, signal in your spectrum, and then you will label that quantum number, and you have an Excel table, and you could plot that frequency versus quantum number and do a trend line. But a trend line is not very nice because it doesn't give you the uncertainty. It gives you M, gives you the slope, but it doesn't give you the plus or minus standard deviation of that slope. So what you'll do is a linear regression. And there's a video on Blackboard about linear regression to kind of introducing that topic to you before you need it. Okay, let's do the transition equation for Raman. So you see the slope on those J values is 2b. So for Raman, we have a delta J plus 2. And so here, everywhere there's a J, we put up J plus 2. So that's where we end up with the J plus 2 and J plus 3. So then we multiply through. And once again, the b squareds cancel. I have 5 b times j minus one of the b's here. So I'm going to make that 5. I'm going to cut that down by 1 and make it 4. And subtract this one over here. And so I have 4b times j plus 6b. So if I divide 4b out, I'm dividing 6 by 4 or 3 by 2, 3 halves, right? And so that's where the 3 halves comes from. I pulled the 4b out front, j plus 3 halves. And so once again, we have that information with the mass of the molecule and the bond length from Raman spectroscopy 2. Only this case, we would solve for the slope with respect to j, and then we would divide that slope by 4, and then we would have the rotational constant. Okay. So those are your transition equations. And remember that transition equation tells you the horizontal, it's the equation for where these peaks show up on the horizontal axis of a spectrum. So everything we've done so far, this is coming to play with real spectra. We have this transition equation, and where do the transitions show up? It's where those peaks are in the spectrum. Okay. All right, so let's take a Kahoot to kind of cement this information. So we haven't done this. Have we done this semester yet? I don't think so. So let's go. Like that. All right. All right, so let's go over there. All right, like the music. More volume, more cowbell. There we go. All right. While you're waiting for others to come in, you can adjust your hats and facial features, whatever. Unofficial prizes for the best one. All right. So what have we got? 5, 10, 15, 20, 22. One more. All right, we're there. Let's go. All right, so if a molecule lacks this, it will not have a direct absorption rotational spectrum. Woo, nice and fast. Good job. Someone scratching their head. Yes, okay, good job. If you ever get like 100%, I'll take a picture of you guys. All right, so let's go next. Let's see what was the fastest thumbs. All right, number 2. Which of these molecules will have a direct absorption rotational spectrum? So we have N2 in red, CO2 in blue, methane in orange, and water in green. Okay, you got a split here. Pure rotational spectrum. So I talked about CO2 being a greenhouse gas, but it's because it has ro-vibrational motions. So it's both the rotation and the vibration acting together for CO2 to be a greenhouse gas, but it's symmetric, doesn't have a permanent dipole, so it doesn't have a pure rotational spectrum. So that's actually, CO2 would be much more of a greenhouse gas if it did have a dipole moment. So it's really good that the carbon's in the middle and the oxygens are on the outside. If you swap the carbon and oxygen and just like stick a carbon on the end of an oxygen molecule, then it would have a pure rotational spectrum and it would absorb even more light in the infrared region and heat up the Earth even more. Okay, and then N2, no, it doesn't. It has a pure Raman rotational spectrum, but this is direct absorption, so we're good. Okay, good job. Third question, which of these molecules will have a direct absorption rotational spectrum? So I'm just asking you again, different molecules. Do you get the hint? What was the hint?
The
nail polish, right? Yeah, acetone. Yeah, that's right. So you can look at the image. It says, no, sometimes it says show media here, but kind of a spread across the board here. Ethane, again, no permanent dipole moment in ethane. No permanent dipole moment in acetylene. So carbon-carbon triple bond with 2 hydrogens on the end, linear molecule, symmetric. So it doesn't have a pure rotational spectrum. And neon's not even a molecule, simple atom. You can't even tell neon's rotating. So it does not have rotational motion. It only has translation. So X, Y, and Z, it can move. It can't rotate, and it can't vibrate. Does that fit with the 3N total degrees of freedom? There's one atom, and there's 3N total degrees of freedom. So yeah, translation X, Y, Z. Okay. So let's see. All right. Question 4. What are the rotational selection rules for absorption and emission? Rotational selection rules. Come on, perfect score, people. You got it? Almost. Yep, it's the plus or minus 1 here. So the selection rules are always the delta quantum number. So if I'm asking them for a selection rule, it's got to be like a delta J if it's rotation. For vibration, it would be delta V. So delta V equals blah, blah, blah for vibration. In fact, we did that last time. What was it? Delta V selection rules for infrared. Plus or minus what? You think of the harmonic oscillator, it was very similar to the particle in a box. What is the selection rule for particle in a box? Delta N equals plus or minus what? 1, 3, 5, 7, 9. So the vibration of harmonic oscillator also 1, 3, 5, 7, 9. But when we add anharmonicity, what happens? It breaks the symmetry and all of them. Delta V equals plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Because of anharmonicity, it's not a symmetric harmonic oscillator anymore. And now for rotational motion, we can use the angular momentum argument that it's just plus or minus 1 only for pure absorption and emission. And then for Raman, it's 2, plus 2, minus 2, or 0 for Rayleigh scattering. Okay, so just reteaching that. That's good. So anyway, but the bottom line is that all the selection rules are always delta quantum numbers, the change in quantum number that we're looking at to see what's allowed. Okay. And last question. What is the spacing between the rotational Raman lines? Okay, kind of a big spread. So again, what do we mean by lines? Those are lines in the spectrum. So this is where the peaks are. And so in the rotational Raman spectrum, the peaks are separated by 4 times the rotational constant. In the absorption and emission spectrum of a rotation, what would it be? 2b. Yeah, so the spacing between the rotational lines in the direct absorption or emission rotational spectrum would be 2 times the rotational constant. In Raman, because we have delta J plus or minus 2, we have a bigger spacing in the rotational spectral lines of 4b. Let's see who our champions are. Dun, dun, dun. Yay. This looks like a British judge. Okay, good. Hey, Pumpkinhead. Good job. Very nice. It's kind of an October-y thing. Yeah, it's good. All right, so y'all have a great day. This was fun.